All right, I'm back for section 5.4. Section 5.4 is, for some people, maybe the hardest section all year. Not for everyone, though. And basically, just because it's, for lack of a better term, it's word problems, right? And word problems I know often cause some trouble. They're hard to set up. As in most word problems, as you're learning them, I think the hardest part is setting them up. The calculus is not going to be too hard. The calculus that we're going to apply is going to be pretty straightforward. So these are called optimization problems. Optimization. We're trying to optimize something, often also called min-max problems. So you see strategies here for solving min-max problems or max-min problems, where you're trying to minimize something or trying to maximize something. We've now looked at the derivative and how the derivative relates to a function and how the derivative can tell us the minimum points and the maximum points, both local and global, of the function. So we're going to basically set up word problems here and solve them and try to find minimums, maximums. So I'm just going to walk through this really quickly. You can pause it right now, copy this down, write it down. These are just the strategies. Basically, what I'm going to do in this video is just do example problems. Can't really walk you through strategies. I can do examples. It's a little trickier to teach than others, I think, but I'll give you that. So the idea is we're going to try to set up an equation, right? So you identify the information, determine your variables. You develop some sort of model, draw a picture. Pictures are very helpful, give you what those variables are. And then you come up with some sort of equation based on the question that needs to be minimized or maximized. The key thing is using one variable. This might sound funny because later on we're going to actually do equations that have more than one variable in them, and that's okay. All your life in math has been one variable, right? You can only solve for one variable. Later on we're actually going to be able to do two. So you're going to have, when you start these, you're going to have two variables in them, or maybe three, and you got to get them all related to one. Most of these problems will have a domain. So we'll have to look at the domain, minimum value and a maximum value for the domain. Once we have this equation in the domain, we want to find the critical points and the endpoints because that's where the minimums and maximums are, right? Boom, 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 boom. We learn this. Minimums and maximums occur either at endpoints or at those critical points. And then solve the equation. Make sure you interpret your results at the end. And answer the question. Seems silly. Make sure you answer the question, but sometimes you get X equals and you're like, hey, I'm done. I'm all excited. But that wasn't the question. The question was find the area or something like that. So I'm just going to do some examples. And here we go. I'm going to bounce around a little bit. So this first question, I'll just let you see it. There's 4 different questions here, actually. 5. I'm not going to do all of them, I don't think. You can look in the book for more. Plus, we're going to go over lots of problems. So the first problem says an open top box is to be made by cutting congruent squares from the corners of a 20 by 25 inch sheet of metal and bending up the sides. What is the maximum possible volume of this box? So let me draw a little picture of this. We got this rectangular thing that, if you remember, was 20 by 25. 20 by 25. We're going to cut squares out of the corners. It wasn't really specific, but the squares need to be the same size. We're going to cut squares out of these corners, and once we cut the squares out of the corners, they're gone. I know it might be hard to visualize this, but you can fold up, fold up, fold up, fold up. You can try it if you want, and you get a box without a top. So I always, whenever I do this problem, I always write down what I'm trying to maximize. We're trying to maximize the volume the box. I always write it down. And then before I get going in the problem, I just think about normal formulas that I need to know. A box is going to have a volume of length times width times height. The fact that it's an open box does not matter because we're not looking at surface area or anything like that. It's the volume doesn't change. So it's just length times width times height. So, like most problems, you need a variable. I'm going to call that X right there. So I call that X. All these corners are X's. They're all X by X by X by X. We're going to cut these out, and we're going to go from there. Okay? So the volume of this shape is the length, which is that green line right there. How long is that green line? Well, it's the 25 original, but we cut out 2 X's, right? So it's 25 minus 2X. The width is this one right here. Same reasoning as 20 minus 2X. And then the height of this box, when you cut those X's out and you fold it up, the height becomes those X's. I know that might be hard to visualize. If you can't visualize, I would actually suggest taking a piece of paper and doing it. You'll see it. So this is my volume. Really, I've done the hard part of the problem, believe it or not, because now I'm going to try to maximize this. There is a domain issue. So domain, always really important. So since I've picked x to be my variable, the smallest x can possibly be is 0. And it really is probably an open 0. Not really important. You can check those endpoints anyway. It's probably not 0, right? Because then there's no box. I can't fold it up. And the other endpoint is, I think, 12 and a half. The reason it's 12 and a half is that long side is 25, so I can't cut any more than 12 and a half out and make a box for the same reason. All right, so I'm gonna multiply this out, make sure I don't make any multiplication mistakes here. So we're gonna go volume equals 500, and then I got a minus 40x and a minus 50x, 25 times, yeah, minus 40, minus 90x, plus 4x squared, and then times x. Volume equals 500x minus 90x squared plus 4x cubed. So there's my formula for it. So right now, if you said, hey, I want to cut a box out where the corners are 1, you just put 1 in there for x. You get 500 minus 90 plus 4, and you got your volume. Boom. You could do it for 1 or 2 or 3. But we don't want to do it for others. We want to figure out which one gives me the maximum volume, and that's what the calculus does for us, right? It's going to find these critical points. So I take the derivative, which would then be 500 minus 180x plus 12x squared. Do a little quick math here. Yep, okay. I don't know. This is, what I need to do now is set this equal to 0. I might try to factor it. I'd probably just use the quadratic, to be honest with you. It's just, I think, a little faster than trying to. So I'm just going to use the quadratic opposite of b, which would be 180 plus or minus the square root of b squared minus 4 times a times c all over 2a. And we hope a lot of these problems come out nice. Not all of them, though. So you can use your calculator just to add, subtract, multiply, and divide. So I'm going to go 180 squared minus 4 times 12 times 500. And I'm going to take the square root of that and hope I get lucky. No, it did not. 91.65. Check something real quick here for you. Hang on 1 second. Yep, okay. So anyway, over 24. Now I'm going to find my two answers are 180 plus 91.65. So much for nice answers. I just want to make sure I didn't make a mistake there. 11.31. And then I'm going to go 180 minus 91.65. Divide that by 24, and I get 3.68. All right. And I'm just checking, and yeah, they're good. So, oh my gosh, I made a big mistake. You guys caught that though, right? Hopefully you caught that. When I was looking at the domain, I was using the 12 and a half from that 25, but I should have used that domain from right there, which is the 20, which would have made this actually a 10. But you knew that, right? So that's going to change this because I think that answer is not going to be in my domain right now. So what I'm going to do is draw my little number line, throw in my little 3.68, a little number to the left of 3.68 into the derivative, which is probably best right here. So we put a number like 1 into that derivative. 500 minus 180 plus 12 is a positive number. You put in a number like 4 into that. 500 minus 180 times 4 plus the 12 times the 4 squared is going to be a negative number. You can just check that on your calculator if you don't believe me. So we got a maximum at x equals 3.68. So now it's not necessarily the answer. We're going to go back to the original problem, make sure we answer the question. It says, what's the maximum possible volume? So we're going to come back here and we're just going to take our volume formula, which was 500x minus 90x squared plus 4x cubed. We're just going to stick that 3.68 in there, and I'm going to hope my book has it so I don't have to just do it for you. Yeah, it's 820.58. That's kind of the process. With min-max, I'll do 2 more. If that's enough for you, you can pile in and just try some examples. The first couple of times they're all a little different. It's all really about setting up the function before you take the derivative. Next question says you've been asked to design a 1-liter can shaped like a right cylinder. Find the least amount of material you can use. So I got this right cylinder, and it holds volume, 1 liter, which is a unit of liquid, right? So I guess I should bop that over into 1,000 cubic centimeters, which I probably should have known. Just so you know, I'm going to tell you that number. Nothing, something I would expect you to know. So the volume is 1,000 cubic centimeters, and we're trying to remember the question said. You've been asked to design one of your find the least amount of material. So what we're trying to do is minimize the surface area, because the surface area is the amount of material. Just making sure there's a top on it, which there is. Sometimes these problems don't have tops on them, so just double check there. So I'm going to throw in some variables. We're just going to call that R and call that H. So notice the volume of this thing is pi r squared h. We're trying to minimize the surface area. The surface area is around the sides, top and the bottom. So it's 2 pi r. Is this? No, let's try that again. That would have been really bad. The area of the bottom, which is pi r squared, but there's the top also, so there's 2 of those. And then you get what's called the lateral surface area. And that lateral surface area, if you think about the opening up this can, it just makes a rectangle. And the width or the length or whatever you want to call it of the rectangle is the circumference of the circle, and the height of the rectangle is just the h. So that's called lateral surface area, a little geometry term you probably did, probably been a long time now. So 2 pi r, which is the circumference times the height. So this is what we're trying to minimize, and this is a common problem in here. Notice I've had to introduce pi, r, and h. This problem I just introduced an x, right? So there's only one variable, but I've had to introduce r and h. But I can't find the derivative of something with 2 variables in it, so I have to get this to 1 variable, okay? So what I'm going to do is use this formula here, which is the 1,000, the volume, pi r squared h, and just solve this for h. And I get that. And then I have something to plug in for my h right there. You could solve for r also. I think that's uglier though, because then you get a square root, but it'll work. So now I go back to the surface area. I get 2 pi r squared plus 2 pi r times my h, which is 1,000 over pi r squared. So again, that's kind of the hardest part of the problem. The derivative will be a little messy here for sure. So I'm going to simplify this. So surface area equals 2 pi r squared plus, let's see, this is going to be 2,000. Pi is going to cancel, 1 r is going to cancel, so over r. So now I'm ready to take the derivative, because that's what I'm trying to minimize the surface area. So the derivative is 4 pi r minus 2,000 over r squared. Remember that this is 2,000 r to the negative 1. So its derivative would be negative 2,000 r to the negative 2. We're going to set that equal to 0 and solve it. Find my critical points. I got to check my endpoints too, which we'll deal with in just a second. I'm going to multiply everything by r cubed, or r squared, sorry, to get rid of that denominator. So I get 4 pi r cubed minus 2,000 equals 0. I get 4 pi r cubed equals 2,000. I get, let's just do this, r cubed equals 2,000 over 4 pi, which I can simplify to 500 over pi, or r is the cube root of 500 over pi, which is just a number. I know it's not nice, but it's just a number. And then I'm going to go cube root of that number is 5.42-ish. So now we want to make sure this is a minimum maximum. You can, we can worry about endpoints, but you don't really have to worry about endpoints either to some extent. You do have to check it, but the endpoints in this problem are open, right? Because open means there's no can. Like if the radius is 0, there's no can, or if the radius is infinity, I guess that is technically the other endpoint, right? Then it's other. So you can just do the plus minus thing, and you'll see, and I'll show you something here, watch. So if I put in a number like 1 into the derivative, here's the derivative. 4 pi minus 2,000 is going to be negative. I put something like 6 in. Just stay close to it. You don't have to worry about the other endpoint. And you're going to get a positive number because that 6 cubed times 4 pi is going to be bigger than 2,000. So this is a minimum at r equals 5.42. Notice if there's only one critical point, you don't have to check endpoints. Just figure out if it's the minimum or maximum, you're done. Because you can't think about this thing only turns once. So if this goes down here to a minimum, goes back to a maximum, the endpoints are not going to matter for minimums. They would matter for maximums for sure, but they don't matter for minimum. Let's make sure we answer the question. The question was, find the least amount of material. So we actually have to find the surface area. So remember, I had a formula for surface area, which was 2 pi r squared, 2 pi r squared plus 2,000 over r. Just plug that 5.42 in there. I'm just going to tell you what it is because that's a little silly. Maybe if I have it here. Oh no, it just gave me the dimensions, never gave me the number. All right, I'll just do it then. So we have it 2 times pi times 5.42 squared plus 2,000 divided by 5.42. And I get 553.58 surface area, so centimeters squared. So there are 2 examples. There's a couple other examples in the book. There's some cost examples in the book that I probably wouldn't look at. These are the best 2 examples. These other ones are kind of similar, but I think I'd rather have you just kind of try these on your own. They're all different. So even if you see more examples of mine, you probably won't see the exact same problem. You might see the exact same problem in the book, which is different numbers, but typically they're just different problems, right? So you have to come up with setting up the equations. So I'm going to leave those to you. And then the homework, I'm going to actually send you the homework assignment, the homework answers on Wednesday. Let's see, I'm working ahead here, but this is on a Monday. We're going to get this, so you can see those. So you'll have more examples. You'll see plenty. Just do the best you can. If you struggle with them, look at my examples when you see them on Wednesday, and then keep practicing.